This is part 3 from the first section of chapter 13 called the Trapezoidal Rule. So, earlier in the section, this diagram was there to explain the concept of approximating the area underneath a curve by using different rectangles. So, in this case, if we use the height of the rectangle to be the left side of each interval, then it creates these rectangles, and that would be considered for this particular function an approximation for the area under the curve, but it would be an under approximation because these rectangles are lower than the curve, and we leave out this lighter shaded piece here, but still gives approximation using rectangles. Okay, if you take the right side of the interval as the height, and the function's increasing like it is here, then this would give us an approximation for the area under the curve as well, but it gives an over approximation because these pieces right here are above the curve. All right, so this is a rectangular approximation method, sometimes called a Riemann sum, because the mathematician who discovered it or made it popular had the last name of Riemann. But they're just ways to use geometrical shapes like we have been doing, rectangles, to approximate area under the curve. All right? A third type of approximation is what we're going to do, and that's the trapezoidal rule. So in the trapezoidal rule, you're going to be making trapezoids. So one usually side of the trapezoid, one base, is slanted. All right? So you're taking, like, for this section, you're taking this y value height and this y value height and connecting it with a straight line. This would give us a slight over approximation. You can see a little bit area on top, but for this particular curve, those trapezoids fit that very well. All right? So in this one, we would be doing 1, 2, 3, 4 different trapezoids, and the more trapezoids you do, or the more rectangles that you do, the better the approximation becomes. Okay, so then this is the general formula for how you would approximate an integral, the area underneath the curve, using the trapezoidal rule. All right, so let's just notice a few things, and then we'll practice it. We'll see it more, maybe change this slightly into a different format that I think makes a little bit more sense. But this is 1/2 b minus a, and b minus a, if you notice, is the width of the total distance that you're integrating. Okay, so lower bound to upper bound. So if you do b minus a, it gets you that total width. And then you're dividing it by the number of trapezoids that you're using. So if your total width is 2, so if this was like 0 to 2, and then you wanted 4 trapezoids, you divide 2 by 4, and each width of each trapezoid would be 1/2. That makes them all the same width, the uniform width there. And then this is the height of the first trapezoid. This is the height of the last trapezoid. Probably when we set these up, I'll put this last piece on the end, just so it makes sense sequentially. And then this is twice all the heights on the interior trapezoid. So when we see a graphical example of that, I think we'll be able to see that formula. All right? So again, this piece right here is dividing the interval from A to B into however many equal sections. So that's why that part of that formula exists, and then you're multiplying that piece by all of these particular heights. Okay, so that formula looks like a lot, and it is, but let's try to apply it to what we see right here. So example 8 says, estimate the area under a curve over the interval from 4 to 12 with x and y values given in the following table. All right, so we're going to estimate this area given a table, not a function this time, but let's take a look at the graph that we show here. All right, so we're going from 4 to 12, and how many trapezoids do we have? 1, 2, 3, 4. All right, so we've divided it into 4 different sections, which makes the width of each of those trapezoids equal to 2. All right, So if we did the formula b minus a, 12 minus 4 would be 8. 8 divided by the 4 intervals would give us that width of 2. Okay? So if we wrote this out this time, here's what this would look like. So first of all, that 1/2 in the formula. 1/2, and then if we're showing it like the formula has us do it, so times b minus a, 12 minus 4, divided by how many intervals we have, how many trapezoids? 4. Okay? And then we multiply that entire thing by the first height plus the last height, but I'm going to put that in at the end. So here's our first height. What's the value at 4? Well, it's 5. So there's 5. And then plus, we're going to use this height on this first trapezoid, trapezoid 1, but then we use it again as a height on trapezoid 2. So that height gets used in 2 different trapezoids. That's why there's 2 times every value that's on the interior of our interval. Okay? So the height at 6 is 13. The height at 6 is 13. So again, we use that height for trapezoid 1, but we also use that height for trapezoid 2. So that's why we're multiplying it by 2. So that 13 gets multiplied twice. Same thing happens to this height at 8, right? This height of 10 is part of trapezoid 2, but it's also the height of trapezoid 3. So we're going to use it 2 different times. So 2 times that one as well. All right, right here at 10. At 10, the height is 3. We see that on our graph. And that is that's the height of the trapezoid of the third interval here, but it's also a height of the fourth. So we're going to use it 2 times. So that is also in the double interval there. So 3 is that height, so plus 3. And then that is my last interior value, right? This is an exterior value. This is an exterior value. Those ones only get used 1 time. All right, so that's the last of my interior values. So that parentheses ends. And then I have to add just one of this outside height. So at 12, the height is 4. Okay, so we have that right there. Okay, and that is all of the trapezoidal rule. But we were given a graph here. We could visually see that. That made it a little bit easier. But let's just do this calculation. 1/2 times, again, we've already done this, but 12 minus 4 is 8. 8 divided by 4 is 2. So that's just going to end up being 1. But then we can clean this up. We can use a calculator if we need to. But let's just show this. This is 5 plus 2 times 13 is 26. 2 times 10 is 20. 2 times 3 is 6. And then plus 4. Okay, so if I was kind of showing that out, that's what that would look like. 1/2 times 2 is just 1. It won't always be that way, but in this case it works out that way. Now let's do this. Let's do 26 plus 20 is 46. 46 plus 6 is 52. 52 plus 5 is 57. 57 plus 4 is 61. And so in this case, the trapezoidal rule approximates this value to have an answer of 61, and we'll just say units because there's nothing labeled, squared. All right, so the total area under the curve using the trapezoidal rule, or using 4 different trapezoids here, gets 61 total units. Okay, so that's the trapezoidal, nice visual way to see the trapezoidal rule, but let's do it in a few different ways as we go through these examples. So we're just going to apply that particular strategy, that particular rule, to different examples that give us the information in a few different ways. Okay, example 9, much shorter, much less there. It says, estimate the area under the graph of the function e to the x over the interval 0 to 1, so just a width of 1, but we want to use 5 different trapezoids. All right, so if we set up, right, if we did the b minus a divided by n, it would look like this. b is 1, minus a, which is 0, divided by n. n is 5, so that is right there. Okay, and then we have 1/2 of that. And then we have to multiply it by all the different pieces. So if we wrote this out and created a graph, it might give us a nice visual. But let's just think about this using what we know about the x values. So if we do 1 minus 0, that's 1, divided by 5, it's 0.2. So every 0.2 is a new trapezoid, all right? So the very first height that we have is the very start of the interval. That would be when x is 0. So e to the 0 is our first value, e raised to the 0, which that ends up being 1. But then we say, so that's the left exterior point, plus now we're on interior points. So we're going to have 2 of them because they share different trapezoids there. So 2 times, and what's the width of each interval? It's 0.2. So my first interior point is when x is 0.2. So that would be e raised to the 0.2. All right, move over one more interval. That's still on the interior, so that's e to the 0.4. Do that again, move over one more interval, e to the 0.6, okay? I know that's still an interior point because I know the exterior value is going to be when e equals 1. If I move over another 0.2, that's plus e to the 0.8. Okay, my next interval is going to be, another 0.2 would be e to the first power. So I know that's the exterior point. So I'll close this off because my very next one, last one, would be e to the first power. Okay, so that's what we have. This ends up being 1/2 times 1/5. So this is 1/10 times everything that we see here. And if you wanted, we could do that on a calculator. Let's just show that. It's going to be e to the 0 plus 2 times those plus e to the first. So if I show that on a calculator, let's get there, that would just look like this. So e to the first, or e to the 0 power plus 2, and then times, oh, I got to get out of the exponent here. Let's clear this out. Okay, so e to the 0, and then plus 2 times e raised to the second, or the 0.2 I should say, e raised to the 0.2 plus e raised to the 0.4. Let's get there. So plus e raised to the 0.4, and then plus e raised to the 0.6, plus e raised to the 0.8. Kind of a lot to put in there. That's my last interior point. So then I'll close that off, and plus my final exterior point, which was e raised to the first power, because that's the end of my interval. And that's going to give me a value of 17.24. All right? So this trapezoidal approximation gets us an area of 17.24. Or if we were just going to 3 decimal places, we would say 17.2 units squared. All right? So that gives us this piece right here. What I didn't do, though, is multiply it by our 1/10. So let me finish that out right here. So this is 17.2. And so we go 1/10 times that. So we still have that value there. And so now let's go times 1/10 is 0.1. So let's do that. And our total area would be 1.72 units squared. Would be the total area underneath the curve. And that makes sense. It's a smaller area because we are just going from 0 to 1. So just a very small interval there. Okay? So this piece right here was the 17.2, and then it needed to be multiplied by that 1/10 from that piece of the formula. Okay, so that would be an example of how you could get those values from a function. You would just be plugging in those different interval values based on how wide your total span is divided by how many trapezoids you're asked to use or decide to use. All right, this one is similar, except for it's just got a function graphed for us, and it's kind of a wavy function. It's not real smooth, but it's modeling a situation. But we can still use the trapezoidal rule to give an approximation for that. So the cross-section of a river is shown here. If the water is flowing at 0.8 meters per second, use the trapezoidal rule with 7 trapezoids, so that's key, that's our end value, to find an approximation for the volume of water passing this point in 1 minute. All lengths are in meters. Okay, so it asked us to use 7 trapezoids. Let's look at the total width of the interval. So we go from 0 to 7. So 7 trapezoids, so 7 divided by 7 gets us a width of 1. So if I drew in this first trapezoid, it would look something like this. So 0 to 1, I'd go up to that first point, up to here, and that is the trapezoid we would be finding to approximate the area under the curve. That's our first of 7 trapezoids we'd be creating. The second one would look like this, right? It would look like that, and it has also a width of 1. Okay, but we have no table of values here, so we're going to have to get our values from the graph. So let's go ahead and set up our formula. So the trapezoidal rule would say 1/2 times, again, 7 minus 0 divided by 7, which that's just going to get us 1. But then we multiply that by our exterior height, so that's 4, plus now 2 times every interior point we have. And it's quicker because we can pick these values right off the graph. So this first interior point is at B there, and that's a height of 3. Plus my next interior point, that's a height of 1. Plus the next one, let's approximate that to be 0.5. Plus E looks to be at 1 again. F is at 2. And G is up at, that looks like about 3.5. We can approximate that. Okay, that's going to close off my interior points because my next point, my next value is on the exterior. So I close off those interior points. All of those are being used twice, so in 2 different trapezoids. And then the last one only gets used once, and the height at 7 is 4. All right, so that would be our trapezoidal rule to approximate the area under this particular function. And so that would be T is equal to 7 minus 0 divided by 7 is 1. 1 times 1/2 is 1/2 times, let's go ahead and just write this out so we can see what's happening. 4, 2 times 3 would be 6. 2 times 1 would be 2. 2 times 0.5 would be 1. 2 times 1 is 2. 2 times 2 is 4. And 2 times 3.5 is 7. And then so that's 2 times all of those values, and then we still have this plus 4. Okay, let's go one step more and let's add everything on the inside. So we have 1/2 is equal to 10, 12, 13, 15, 19, 19 plus that 11 is 30. So 1/2 of 30 is 15. And in this case, our It's meters per second, so our units would be meters squared. The area under that curve would be 15 meters squared. Okay, so again, trapezoidal rule. You're just using the shape of a trapezoid to approximate the area underneath the curve. And our rule for that is to take the entire interval, so b minus a, divide it by the number of intervals, the number of trapezoids you're going to use, multiply that by a half from our trapezoidal formula, and then this is the first height, so the most left height. This is the most right height, so the two exterior values, in this case they just happen to both be 4, that won't always be the case, and then plus 2 times every height that's on the interior. All right, and you're going to do that for every trapezoidal rule, whether you get it as a graph, whether you get it as a function, whether you get it as a table of values. That process is always the same. So that wraps up section 13.1, which is the intro to integration, and that will allow you to complete the rest of the practice from 13.1.